Hi, everyone. Just wanted to take a couple minutes to talk a little bit about some of the information that we need to know in regards to scatter plots and lines of fit. And we're going to talk a little bit as well about some of the statistics that you can do behind this and how we actually get through that. So, the first thing we're going to talk about today is association. So, the association is really just the relationship between points of data, right? So as you can see on this first one, in general, as your x is kind of increasing, your y is increasing, right? If you were to draw a line, it's generally going up. So that's what we call a positive association. Um, in general, association really is just talking about the relationship between all the points. Okay. So on this one, you can tell that as your x is increasing, your y is actually decreasing. So if we were to draw a line, it would be roughly something like that. Um, and that is a negative association. Now, as you can tell over here on this side, um, there's not really anywhere I can draw any one distinct line that seems to be the best, right? So on these ones, I drew a line that kind of was in line with the points, right? I could draw this line, and you would say, all right, well, maybe I could draw, I could draw something like that line, and you still probably could be like, yeah, all right, that's fair. Um, you don't really know just from looking at it. So this is something we would call no association. So there doesn't seem to be any sort of relationship between the points at all. Um, and we can actually kind of use this to kind of predict what's going to happen, right? So obviously, if there's something with a positive association, we're kind of assuming that as x is getting bigger, your y value is getting bigger. We don't necessarily know how much it's getting bigger by. We're just kind of saying in general it's getting bigger. So this is kind of your broad statement. Like in general, it's kind of going this way. Um, or in general, there's not really anything we can say other than we collected some data and it kind of is all over the place. All right. So if we were to go through something like this and we were to try and predict what this would be, obviously we can say this has a positive association. So as we're getting further along after sunrise, we would kind of predict the temperature would increase. Now obviously that doesn't tell you the whole picture, right? If we probably were to continue on with a graph like this, what's it really going to look like? It's really going to probably do something like that, because after a certain point the sun's going to start to go down, it's going to get cooler. So just because there is a positive association for what we're seeing does not inherently mean that we know all of the details. Similarly, with the second one, the temperature after sunset, again, you can almost kind of see it's almost like a continuation, right? Now we're going down. Now it's a negative association. So before it was a positive, now it's a negative association. And you could kind of predict that as the hours increase based on this graph, you predict it to keep getting cooler. Obviously, that only is valid to a certain point, but we're just saying that based on what we've seen. And then finally, at the end here, we have our no association, right? I can't really make any sort of prediction. I can't really say anything. I can just kind of look at the data and say, all right, after hours after sunset seems to have no particular effect on amount of rainfall, right? If I tried to draw a line, you would say, well, maybe it could really be any of them. So there's not really any association. Okay. All right. So that's pretty much everything we need to know in regards to association. Now, as we kind of move along, we're going to more formalize this. So now we have a correlation. Um, and you're probably looking at this and saying, well, this looks about the same as association. It's just a little bit more specific because we're now specifically talking about a linear relationship, right? So we could fit that trend line that I was just kind of drawing willy-nilly. So in this term, we're talking about a linear relationship specifically, right? So we're fitting a line to the data. And that's kind of the difference between them. They're related, but they're not exactly the same. Sometimes they are used interchangeably, though, association and correlation. So if a scatter plot suggests a linear relationship, you could have a positive correlation, which is kind of similar to your positive association, right? It's increasing. If you were to graph this line, the slope, right, would be a positive slope. So if I were to try and find the slope of this line, m would be a positive number. On the contrary, if you were to draw a line and it had a negative slope, that would be a negative correlation. All right. Um, Ultimately, if you were to have something with no association, right, you would kind of have a line that's kind of closer to horizontal. And that probably means that that's really not a linear sort of function that you should be modeling it with. But that's okay. For our purposes, we're just kind of talking about what it looks like. So if we were to continue on with correlation, what would we say about this sort of correlation, right? We would say this is, if I were to draw a line, it's going down, it is a negative slope. And because there's a negative slope, I would say this is a negative correlation, right? So the slope is negative, so my correlation is negative. Correlation, a negative correlation. Okay? So there's a negative correlation that is going on here. We haven't directly talked a lot about how to identify much more at this point, other than what the difference is. But just know at this point, your goal is kind of like if you had a line, look at the slope. If the slope was positive, it'd be a positive correlation. If the slope is negative, it'd be a negative correlation. Okay. All right. So to kind of recap here, again, your association, right, as it's increasing, it's generally kind of increasing. And negative association, as x is increasing, your y is generally decreasing. Your positive correlation, if I drew a line through it, positive slope. If I drew a line through my data on a negative correlation, it would have a negative slope. All right. So from there, what can we actually do? Well, it's all well and good that I'm just drawing any sort of line. However, our goal now is to specifically draw the best line that we can to fit our data. So, right, our goal is, this line looks pretty good, but how do I know it's the best line for the data? And by best line, really what I mean is I want the line to be as close to as many points as possible, right? I want that distance between the points and the line to be as small as possible, right? So we're going to do something called a linear regression. A linear regression is just the mathematical method that we are using to find and calculate the line of best fit. So the line of best fit, that's that line I was just telling you about. That's the line that is going to most closely match our data. So if I were to pull up Desmos, wrong Desmos, sorry. If I were to pull up Desmos, what would be an absolutely perfect line? Well, if I were to make a table, and I said it was 1, and then 2, and then 2, and then 3, and then 3, and 4, and then 5, right? Now, if I were to try and draw a line through this, see how that's like a perfect line, right? So that would be your kind of your linear, right? Ooh. So this would be, the perfect line for this. Most data in real life is not quite like that. It's a little bit something more like if we had that, and I'm going to turn off. There we go. I'm turning off the line. So really, usually it's not that. Usually it's something more like 3.4, right? And then maybe I only have, 3.9 here, right? So it's not quite a line. It's close, but it's not quite a line. So that's what our goal is. Our goal is to try and find the best possible line for our specific data. Now, what you can do is if you have, a spreadsheet of data, or you've collected information from somewhere, I'm just going to copy this data in. So again, if I want to try and copy non-consecutive spreadsheets, I'm sorry, non-consecutive columns, hold Control while I'm selecting the second one and see how I'm getting both. And I'm going to copy, so Control C. I'm actually using a Mac, so I'm using Command. But if you were using a PC or a Chromebook, you would use Control. All right, and I'm going to go into Desmos. I'm going to Control V, Command V. Right, so I got this graph. Now, obviously, I can't draw a line through every single point. I can draw a line that's kind of close, right? It looks like I have a lot that are in a relatively kind of liney shape, but they're not quite. It's not quite a perfect line in any way, shape, or form. It's pretty good. This is a pretty good data set. But that being said, it's not a line. So what we are specifically going to do is we are going to run a linear regression. All right. So how do we actually run the linear regression? So, I mean, I could use this data set. I just plugged in a bunch of data, so I'm going to use that one. But I'm going to use this operation or function within Desmos. So y1, and that is automatically doing that for me. It is automatically making that. If that didn't work, do shift minus, and that should also work as well. See how it just went down when I did the shift minus. So see how, okay, so 1, and I have to do the little squiggle, the tilde. So what I'm gonna do, and that is shift, and then the button above tab should be that. And I'm just gonna say AX1, and again, it's automatically doing that for me, but if it's not doing that, do shift minus, plus B. All right, and as you can see, I'm getting a bunch of information, and it's automatically graphing my line. All right, so it is automatically graphing my line, and I'm actually just gonna save this. All right, so when I save that, you also should notice that my the link up here, if I were to copy this, the browser, it changed a little bit. So I got that part, so that'll actually be, so that way if I were to click on this link, now it would go directly to this graph. Anyway, so you'll see over here a bunch of stuff just came up when I typed that in. So this is running the linear regression. And that line, that purple line that just got graphed there, that is our line of best fit. So as you can see, it's actually relatively close to a lot of these different points, right? There's a few like this one, right? Like this one's kind of far off. But overall, they're only like that. They're kind of like, that one's only a little. That one's a bit off. That one's, pretty close. That's very close. It's almost on it. A little off, a little off. And it's okay if they're a little off. That's what we're looking for. We're not looking for every single point to be exactly in a line. That's unrealistic. That being said, if you were to try and run a linear regression and they were exactly a line, you'll see, watch what happens. So I'm going to erase that. I'm actually just going to hide these for a second. I'm going to hide that as well. Right, so if I add just a quick table here, I'll show you what happens if I add a table. And I don't know, 1, -1. Oh, no, let's start at 9. Okay, so 1, 9, 2, 8, right, 3, 7. So as you can see, I'm going down 4, 6, so on and so forth, right? If I tried to run this linear regression, and I'm going to do y2 now because see how my graph, my table is now y2. Again, the tilde. So I did just do A and B, so I'm actually going to use different parameters. Oh, no, let's do the same thing. Nope, not A1. Sorry, A2. Plus B. Now, you'll see what has happened here is I got a line that goes directly through all of my points. And that's because all my points were actually in a line already to begin with. So the best line for that set of points is just the actual line that goes through it. So I'm going to hide that for a second and go back to my old one because that's a little bit more interesting. But anyway, so you'll see a bunch of other pieces of information just popped up. You'll get something called statistics, which has an R squared value, which for our purposes in this class, we are not going to be looking at. That's actually something called the coefficient of determination, but we're not going to worry about that. We got the R value, which is something called the correlation coefficient, which we are going to look at. And then we got A and B. So A is, again, if you were to draw a line, right, A would be your slope. So that's just your slope. Then we have B, and this is going to be your y-intercept. All right. So that's all that we've gotten. We've got a lot of information here, and this is just if we were to try and graph our line, right? So if I were to write out my actual equation of my line of best fit, you would say y equals 1.45669x minus 4.24409, and I guarantee those numbers are rounded. But ultimately, that would be our line of best fit. Okay. Now, you'll notice one other thing came up called residuals, and I'm going to get to that in a minute, but let me just finish talking a little bit about the correlation coefficient. So I told you we are going to use the R value. So if I pop back over here to my spreadsheet, we're going to talk about the correlation coefficient, the R value. So now when you run that linear regression, you're always going to get that R value to pop up. And it is going to be a number between -1 and 1. And those are going to indicate two things: the strength and the direction of your relationship between your two variables, okay? So it gives you two pieces of information. Piece of information number one is it positive or is it negative? All right? If it is positive, it is a positive correlation. And if R is negative, it is a negative correlation. The other piece of information that you're going to get is that really the number itself, right? So we're kind of dividing it into two parts. We're dividing it into positive or negative, and then we're dividing it into the number, right? So the positive or the negative, that just tells you if it's a positive correlation or a negative correlation. And then the number, all right? So the number component just tells you how strong of a correlation this is. So a number that is really close to 1 or really close to -1, these are the strong correlations. Strong. And then if you have something like very close to 0, this is a pretty weak. Well, actually, to be honest, if it was exactly 0, there'd be completely no correlation. But I don't even know how that would work mathematically. But pretty much anything, close to 0 is a weak correlation, right? So like a 0.2, a 0. A negative 0.14, that's pretty low. And there's no defined hard line that you have to have in terms of what is a cutoff or a strong versus like a medium, or moderate, I should say, versus a weak, right? So it's kind of a continuum somewhere between 0 to 3.3 or 0.4 kind of falls in your weak. Your moderate's kind of your 0.4 to your 6.5 ish. 6.5 is like kind of like that weird, up to 6.5, 7. Anything above 7 is usually pretty strong. The only time that you could say it's a relatively a weakly strong or something like that, whatever. As long as you kind of get the point across that closer to 1 or closer to -1, it's a strong relationship. Closer to 0, it's a weaker relationship. Okay, so do your best with those. So for example, right, this is really close to 1. You can see all the points aren't very far off of your line. So it's a very strong, and it's positive, right? It is a positive R value, so it is a positive and strong. correlation. When it's close to zero, it is a weak correlation. It's very weak. It's a weak negative correlation, technically, right? It does have the negative out front, but really it's just weak. So something like this, if you get something like this, I mean, we call it a weak negative correlation, but really, what is it telling you? It's telling you that a line's probably not actually even the best thing for this. And then finally, your -1, if it's closer to -1, now this is a really good correlation. But the closer it is to -1, the stronger it is. And again, it's a negative correlation. Right. So if you were to predict something like this, a 0.1, very weak. It's weak. It's positive, but it's weak. And then a -0.6, I would say that's a moderately strong, a moderate negative correlation. Kind of in the middle, right? 0.5 might be the exact middle, but this one, is pretty close. Okay. So for right now, this is just telling you exactly what we're dealing with in terms of our line of best fit. Okay, so this is kind of just telling you like how good it's doing and how good of a correlation we have. Obviously, the higher, the more correlated we're anticipating the values to be, and you kind of think of it as maybe it might be a slightly stronger predictor. But we don't want to fall too dangerously low into that trap because sometimes things don't even follow the sort of line that we're looking for, right? So sometimes things aren't even really aligned. They just look like they would be. And that's where our next piece of information comes in. And that's something called residuals. So the residual itself is just the difference between the y value and the predicted y value. All right. So what do I mean by that? It's this distance. This is my residual. So I actually had the point up here, but I predicted based on my line that it would be here, right? Or I actually had the y value down here, but I predicted it would be up here. Now, it's really showing how well the linear model is fitting the data. So if they kind of are randomly distributed like this, if I move my face, they're kind of all over the place. You have a couple above, you have a couple below. They're not all just like clustered. If they're randomly distributed like that, that actually means that the linear model is like a pretty good fit. If you see like a pretty distinct pattern, and by distinct pattern, I mean like they're all, except for one on one side, they're kind of gradually changing. That's a different discussion point. That might just mean that a linear model is not even really a good fit. Okay. So and the reason behind that is sometimes things look linear at small values, but as you continue on, they're actually something more like exponential, or they're more like a quadratic. So the residuals is just our way of testing whether or not something is actually fit by a linear model. So for example here, the scatter plot with the line suggests that there's a negative correlation. And the residual plot, when we look at that, see how it's kind of all over the place? So the linear model is probably pretty good. All right. So if I were to look back here, if I were to go to Desmos and look back here, you can see I can easily just plot my residuals by hitting the plot residuals button. All right. Now, it'll automatically do it for you. So that's a positive. And it's these little black dots. Now, this one up here is a little bit of a cause for concern. That point potentially is an outlier. I don't know. So this point is a little bit of a cause for concern, but the rest of these points, you see how they're, we have a couple below, we have a couple above, this one's below, a little below, and they're all pretty close, except for that one up there. That, again, is just indicating to me this might be an outlier. But ultimately, this is a good fit, right? Like, it's not clearly obvious that there's a different pattern going on with the residuals. So that's all we're looking for in terms of the residuals, all right? Now, we're almost done. Oh, one more thing to talk about, by the way. Um, so ultimately, as you can see, this is a 0.7779 R value. So this is a pretty strong um, correlation, positive correlation. This one, see how it's -1? That means it's a perfectly fit by a line. So if you were to try and plot the residuals, what are they all going to be? Um, they're pretty much all zero, right? And except for these, which are 0.00000000, blah 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 blah, which is really just a rounding error, right? Um, so that's just what happens when you have the actual line itself. Okay. So we don't really have to worry about them other than you just want to look at them and say, yep, they exist and they're not directly forming a pattern. If they did form a pattern, all you would say is, you know what, they're forming a pattern. I don't think this is a good fit. And most of the time, when you notice that there is something like that happening, it's usually, pretty obvious on our end for what we're dealing with. Um, but that being said, it's always good to check. All right, couple more pieces of information. We are finally going into the kind of what happens next, right? So we talked a little bit about forming and creating our line of best fit, how to do that on Desmos, but now you're probably asking yourself, why is this useful? Well, we kind of were hinting at it when we were talking about the residuals with the predicted value, right? So you might want to use this line to try and predict values. And when you're trying to predict values within a data set, right? So that is called interpolation. When you're trying to predict values beyond a data set, that is extrapolation. So interpolation would be something like, we kind of have data between the years, like in this example, 1975 and 2003, right? So we kind of have information, but we only have years every we only have data every 5 years. So let's say I want to try and figure out, how much people flew in 1982, right? That's not going to fall on one of my 5 year quotas. However, using my line of best fit, I could try and figure it out. Extrapolation would be, we went until what, 2003. For example, I tried to extrapolate and figure out how much people are going to fly in 2030. Right. So the further you're getting out, kind of the more dangerous it's getting. We also don't inherently know what things are going to be like. Right. So if somebody tried to predict what flying would be like in 2020, that's a totally different value than I'm sure anybody would have predicted because of airline restrictions and things like that. So you do need to be careful. But what can we actually do with these? Well, let's kind of take a look. So if I were to use Desmos to make an extrapolation or interpolation, um, I would honestly just kind of say, I want to pick a different point. I want to just pick a point in the data. So what's my data between? It looks to be between, what's my lowest? A 4. Between 4 and 9 or so, right? So those are my X values. So it's not exactly a huge range. But let's say I want to pick what I think would happen at 5.5. Nobody seems to do that. All right. So what I'm actually going to do is I'm going to add an expression here. I'm going to move it lower. So right below that. So if I plug this in, right, I want to figure out what's happening at 5.5. Okay, so if I'm plugging in 5.5, I'm not even going to bother like doing out the calculations. I'm just going to say I want A times 5.5 plus B. Oh, it's yelling at me. I'm just going to delete that. And I'm going to change that color because I can't see it. All right. And I'm going to label it. All right. And there you go. There's that interpolated point. So I would predict that if my X value was 5.5, my Y value would be a 3.768. All right, so that's what I'm predicting, right? This is my point of interpolation. Now, what if I continued on? Nobody said 10. So what if I predicted 10? And now so this is my interpolation. And then finally, I'm going to do my extrapolation. So I'm going to go beyond my data. What if somebody said 12, right? Maybe that doesn't make sense in context, but I'm just saying what happens if I do 12. So 12. So all I'm doing is I'm plugging in 12 for x, right? Plus b. Oops, b. Sorry. And see how I already have this over here, right? It's kind of expanding beyond. I would say if it was a like this, I would predict that at 12, somebody would have responded with a 13.236. Now, obviously, based on our data, that may or may not make sense, right? If this is a scale of 1 to 10, that's not going to make any sense. That being said, that's kind of the dangers of extrapolation, right? What if all of a sudden, somewhere around 10, it just kind of curved down? We don't know. We're just taking a guess. And that's what we're guessing based on our model. So that's all that we're doing. We're saying, based on this information that I have, if things continue on in this manner, then I would predict that 12, I would have an output of 13.236. All right. So that's all that's happening with extrapolation and interpolation. The final thing I do want to talk about is not necessarily a mathematical thing that you have to do. We just need to be careful. Correlation does not mean causation. Okay, so just because there's a correlation between data points, that does not mean that your x value is causing your y value, right? So a causation, that's just a cause and effect relationship. So a change in one, it's explicitly causing a change in the other. A lot of times you have to carry out an experiment many, 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 many times, trying to control for just about every single other variable that could exist, that to be able to say that something's causing something else in terms of statistics, right? So hours of sleep and test scores. Can we say that hours of sleep is directly causing the test score to be higher? No, no, that doesn't make any sense, because obviously then, right, if I slept forever, I would do amazing on the test. But there's a lot that that's not going to happen. Um, Getting more sleep is not necessarily causing your test score to get higher. It could be part of it, but it's not the whole picture, right? I can't directly say that because I slept more, I'm definitely going to get better. All right, that's what we need to be careful of, right? So another example. As temperature is increasing, there's a positive correlation with the number of beachgoers. That doesn't mean that the higher temperatures is causing the number of beachgoers to increase. Again, could they be related? Yes, of course. There's just more to the picture that would need to be addressed, right? We could talk about the time of the year. We could talk about all kinds of other things. But we cannot directly conclude that it's the only reason. And that's just what we need to be careful of. That correlation does not mean causation. Okay, so that's just about everything that you could ever wish for and hope for in terms of the stats overview. Please, 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 please reach out if you have any questions. Have a great day.